Okay, hello everyone. So we'll start with week 7 content. So we'll be solving some problem related to week 7 lectures that is related to PID controller design for feedback control. So I is my voice audible? Okay, fine. So let us start with questions. So this is the first question. So we have gone through this PID controller and we saw what is the effect of these terms like this integrator, derivative, and proportional term. So basically, uh, this question asks that when Ki, that is the integral gain, in the PID controller is increased, then what is the effect on settling time? So what we know about the effect of adding poles in the closed loop system. Okay, so basically, if this is the S plane, you can say, and when integrator, like if we have integrator in forward path, we add this one, suppose PID controller, and we have plant with this feedback. So the effect of this integrator is that it shifts the root locus towards right. So when it is shifting the root locus towards right, basically, if we consider a second order system, a standards that we have gone through. So whatever type of system it is, we can try to approximate that using a second order system with dominant pole. If there is this complex conjugate pole, otherwise if it is on this real line, then if two poles are close, then we can say, okay, this is kind of over damped system. And if the second pole is far away, then we say, okay, we can approximate that using a first order system. So if we have these type of systems, approximate, basically these are models. So anyway, we are not having a high fidelity model. We are just approximating the models. So in that case, when we are adding this Ki, so since it is shifting this way, so the location of pole is shifting rightwards. Okay, in that case, for second order system, what we know, the root is like minus zeta omega n and omega n root under 1 minus zeta square, if this is a complex conjugate poles. Like, so in this case, what happens? What do we know about settling time? Settling time is 4 by zeta omega n. So this is decreasing if we are adding or if we are increasing the gain related to integral term, then this term, this whole thing will increase. So basically by increasing the integral gain, we are increasing the settling time. Also, one more thing that we can see, that since it is shifting towards right, it is going towards verge of instability. And in that case, since the damping is low, there will be increase in oscillations. So we can say, suppose this kind of response we want for step input, then with increasing Ki, this will be more oscillatory, like this. So peak overshoot will also increase in that case. So this is kind of like some insight about what is the effect of these gains. So this is the answer. And this is also discussed in the lecture. So obviously, I believe that you know this. I expect that. Okay, so we'll proceed to next question. And it says that which of following are not correct. So you have a controller, which is this. So any plant, or you can say system, and there is a compensator or controller, which is GCS, feedback loop, negative feedback. So what can we say about this controller? So this is a, okay. So this is the zeros, minus Z, and minus P is the pole. Okay, this is the thing that we know from here. And this system is like this transfer function is a proper transfer function. This also we know because number of poles is equal to number of zeros. So this one is realizable. This is what we know. Okay. Now what can we say? So it is asking about lead and lag compensator. So when we are dealing with PID controller, we said, okay, so these term like 1 by S, S, to physically realize this. Obviously, if we are having, and how do you define this? This Kp, and if this is the error signal, that is R minus Y, so Kpe plus Ki e dt plus Kd dE by dt. Okay, so this is the input to the plant. Now this input, either it can go directly to the plant or there will be some block which is kind of actuator that will realize the input to the plant. So this U will go to this one and then this will pass the signal to this plant. In that case, we said, okay, so if we write the transfer function, this is Kp plus Ki by S plus Kd S. Okay. So we said that physically realizing these terms is not, we cannot realize this obviously. This is very difficult to realize. So we try to approximate these terms using the compensators. Now, if you are obviously, if you are implementing this in computer, then you can do this. But using a hardware and implementing this is not possible in the for this part, for this derivative and integral. So for integral part, this is like adding a pole at origin. Now, what we say that we'll have one 0 and we'll add a pole near to origin. So we try to do this. In that case, this 0 has less effect because it is far. So its effect on transient is very less and it decays very fast. And then this pole will have some effect which will be approximately similar to what we expect from our integrator. So if we have simple integrator, so there is a pole at this point, and if we approximate this with a pole at this point, little difference will be there in performance, but approximately yes. So we try to approximate this, and since this transfer function is proper, that means number of poles is equal to number of zeros. So this is realizable and this is stable also. Okay. However, this was not stable, this was marginally stable. So in this case, so this we call as lag compensator. And for this one, this if this is minus P and this is minus Z, obviously P is less than Z. Now if we talk about this term, so it is like adding a 0 at origin. We'll say, okay, we'll add 0 somewhat near to origin and we'll have some pole. So we can also, since this one is not realizable, to realize it, we what is done, that a filter is added. So basically a pole is added so that this pole blocks the high frequency component, because when we are talking about control system, what are the like feedback closed loop system? So this is the plant. This plant has some behavior, dynamic behavior, and what we want, that this plant should behave in some particular way. So to achieve that, we say, okay, what we do, we'll have a controller and we'll just feedback, we'll have this output feedback, and then we'll see, like we'll manipulate the input to the plant such that plant achieves that behavior, or plant tries to track that behavior. So in that case, this is one of the objective. And when we are including feedback, so this can be done using open loop also. So we'll just have a plant, and we have some controller, you can say GCS, and we have input, we have output. Basically, controller here means some extra added components, so subsystem, such that plant behavior is modified. Now here at the output, we are not taking feedback of this, so this loop is not there. So this, we can say that okay, this may have some behavior, but we don't know, maybe there is some noise, because of which, because whatever output you are getting, you are observing, that is through sensors. So sensors will have some property that may introduce some noise. So maybe it appears that okay, output is following the behavior, but in actual it is not. Maybe it is because of sensor noise that it appears that output is like having very good property. Also there may be disturbances, so there may be a disturbances acting in the input of the plant or output of plant, that will have an effect on output. But since we are not taking feedback, we are saying okay, we have calibrated this controller or this subsystem so that plant behave in a particular manner, but in actual it is not behaving. That's why we had feedback. So the effect of feedback was like, why we introduced feedback, because we wanted plant to behave in a certain way, also so as to reject disturbance effect, or we can say that nullify the effect of noise. These are also one of the like some of the properties that is achieved via feedback control. So in that case, when we are using this term, this one only. So if this is the controller part, this derivative term, the error signal, if it has some high frequency component, so suppose this error is varying like this. Now, if it has some disturbance, it is varying like this. So high frequency means uh, changing frequently, some kind of that signal. Then in output, that will also be amplified. That can be amplified because it is a high pass filter. So it will have some gain at high frequency and it will amplify at input. There will be large changes due to noise. So in order to block that frequency components, we have these poles. This is the effect of adding these poles. Okay, so basically for approximating this derivative term, we have this controller, or like we have this compensator, and this is we call lead compensator. And for this one, if we have the pole zero plot, so here we have this 0 and we have pole, so obviously that is less than P for this one. Okay, so now we can see what which are the correct and which are not correct. So if GC is a lead compensator, that means Z is less than P. So we have seen here that yes, Z is less than P in case of lead compensator. So this is fine. Now second one is GC is lag compensator if Z is less than P, but in lag compensator we have seen that this P, because this is positive value, so we are saying, otherwise we can talk in terms of minus P also, then we'll say magnitude. Okay, so P is less than Z, but here it is saying Z is less than P. So this is not a correct statement. So since the question is asking not correct, so this is correct. Okay, and then it says angle of GCG omega is always positive if GC is a lag compensator. Obviously, since if you consider Bode plot of this one, so first there is a pole, right frequency 1 by P. Okay, so there is a pole and there will be decay because of this. Like decay means there will be gain will reduce by minus 20 dB per decade. And then because of zeros, we'll have minus 20 plus 20, so a constant line in frequency domain. And for lead compensator, you have first have a zeros and then a pole. So what you have this kind of system. This is the magnitude plot. And if you talk about this phase angle, so it will contribute positive angle, then it will tend like this thing. So this will be positive in case of lead compensator, but in lag compensator, due to pole coming first, like it is having less magnitude, therefore it is not positive. Yes, so this is false and this is correct. Okay, so we'll proceed to next question. It asks, by increasing KD gain, so derivative gain of PID compensator system, the percentage overshoot of compensator system decreases. Is it right? So why is this D term included? So the effect of including D term is that it shifts the root locus towards left of the S-plane. In that case, it is including, like it is introducing some kind of damping, because more towards this left half S-plane, more will be the damping. And if damping is higher, we say that, okay, percent peak overshoot is less, because MP is inversely proportional to zeta. Okay, so this is correct. So now we'll see how we can tune these parameters, this PID, such that we achieve desired response. Okay, up till now we have solved questions so that we say that this is the effect of these individual terms in PID controller. But if means how can we tune those value to achieve desired response, that we'll see in this question. So we have a second order system with transfer function this, and there is a PD controller. The closed loop system has a second order characteristic polynomial with zeta 0.7 and omega, that is 3 radian per second. Okay. So you have this plant 1 by S plus 1, S plus 3. Now We have a controller which is PD controller, so Kp plus KDS. Which is reference, and this is Y. So it is saying that this closed loop system has zeta equal to 0.75 and omega n equal to 3 radian per second. So for this, what do we have to do? We have this, we know the forward loop transfer, like forward transfer function, and we have this unity feedback gain. So we can derive the closed loop transfer function, and that will be Kp plus KdS multiplied by this, because these are in cascade, by 1 plus G into H, where H is 1. Acha, sorry. So we'll just simplify this. Kp plus ds. S square plus Kd plus 3s plus Kp plus 3. Okay, so this is the closed loop transfer function. Now from this, it is saying that, okay, zeta is this one, 0.75, and omega n1 is this. So what can we say? From the standard second order system, we know that the transfer function, like the characteristic equation, we can say. So that will be not equation, because this is not a characteristic polynomial. Okay, so s square plus 2 zeta omega n s plus omega n square. यहाँ पे समझेंगे के, okay, fine. So this is the thing. Now from there, what can we say? That omega n square is equal to Kp plus 3, and 2 zeta omega n is equal to Kd plus 3. So Kp will be equal to, this is 3 square minus 3. I'm writing Kp plus 3. This is 2 now. So this will be 7. And for this one, since we know Kp is 7 and zeta omega n is known, so 2 into 0.75 into 3 is equal to Kd plus 3. This implies Kd is equal to 1.5. So for this closed loop system to have the poles such that this zeta is cos inverse theta, and this omega n, so omega n is the length of this vector, so this is 3, and minus zeta omega n, this will be the location of pole. So corresponding to this zeta and omega n, we have poles for this system, closed loop system, that is minus zeta omega n plus minus j omega n root under 1 minus zeta square. Now for this is one way that we did the similar like thing, but this is one way we did that we have one. Okay. So what we did that we said, okay, this is the transfer function, and we found transfer function equation. Then we equated this with this standard second order characteristic polynomial. So this is similar to this way of doing that. We have zeta and omega n. We'll find the roots, and once we find the roots, we'll say what is the polynomial corresponding to root. So that will be s minus s1 into s plus s minus s2, s1 and s2 if these are the roots. So this is the polynomial corresponding to these roots, and from there we'll get some s square plus alpha s plus beta. So alpha and beta we can equate with this one, kd plus 3 kp plus 2. Similar thing is just that whatever you find easy you can use that one. Okay, so kp value we found out that that is 7 and kd is 1.5. Okay, so I hope this is clear. Then we'll proceed to next question. Okay, so this is a satellite altitude control problem. So we have a double integrator plant. So we know this one, no? Newton's law in terms of rotational motion, that is j theta double dot equal to alpha, where alpha is the angular acceleration, j is moment of inertia, and theta is the angle of rotation. So when we are saying satellite altitude control, so altitude means this angle control of this satellite. So we have this transfer function of the plant that we can write from here, that j s square theta equal to alpha. So theta by alpha is 1 by j s square. Okay, so this is the transfer function plant. Now what is the input to this? So there is a controller, which is DCS, and it is taking the error. So we have this reference. This is a feed forward gain, so that we can have the desired reference. And then this theta is being measured through this sensor, which has this transfer function hy, and this is being passed to this controller. So this is, there is this error between this, suppose theta m, and this is a feedback term. So this error is going through this controller, and this is driving this plant. Now apart from this controller effect, we have this effect of disturbance W, which is acting on the system. So this will also have an effect on the output theta. Now it is asked, so let us see what value is using. So first of all, J is equal to 10 Newton meter second square per radian. And then Hy is 1. So now this converts to unity feedback, and Hr is also 1. So feed forward path is also having gain 1. Okay. So if DCS is equal to Kp, this is a proportional controller. So what is it asking? The range of Kp for which system will be unstable. Okay. So if you see this system, this plant, this is kind of unstable because 1 over gs square, so 2 poles at origin, and we have Kp negative feedback. Okay, and there is one disturbance term also. So this is summation of these two. This is theta. So what would be the output given this theta r and w? The output, if we find the Laplace domain, so this will be theta is equal to this dc. This is dc s by gs square plus dc into theta r plus for this one, this will be again be this 1 by gs square plus dcs. Okay. So loop transfer function is same. Characteristic polynomial. So we have this transfer function, and given this theta r and w, we can find what is the theta. Now, what is the transfer like characteristic equation? We can say that will be js square plus dc equal to 0. So j is 10 s square. Now we have this proportional controller. So dc is equal to kp is equal to 0. So this equation, what is the roots? Root is just on the imaginary axis, because you have s square equal to minus kp by 10. So if you remove this one, this will be root over, and this is negative, so plus minus j omega you'll get, and this will be on this imaginary axis. So whatever be the value of kp, obviously we are assuming that kp is greater than 0. So whatever be the value of kp greater than 0, this is always on the imaginary axis. So it's not on the like in the right half plane. Therefore, for kp less than 0, this will be unstable, because for kp greater than 0, it is on right half plane. Okay. So kp greater than 0, you have this, and if kp is less than 0, we have s square. If this is minus kp, so this will be some positive term p dash by 10, and we have root under this one. This will give plus minus something. So this will be in this one, like two poles, one in right half plane and another in left half plane. So always for kp less than 0, we have one pole which is in right half plane. Therefore, the system is unstable. Now, the second question, just now we solved it. So if kp is 100, then system is, so we have seen that for kp greater than 0, whatever the value it is having, this is negative, so it will always lie on imaginary axis. Now, if it is on imaginary axis, that means that this system is marginally stable. Fine. So that means if we just use proportional controller, this closed loop system is not stable. So then what we need to do, since this is kind of marginally, like this is unstable, and then we have added proportional, so this gives us marginally stable system. We want to move the poles or shift the poles of this closed loop system towards left in the S plane. So in that case, the pole should be this side. In that case, we need to add some damping. So this oscillations, because this is marginally stable, that means the output is kind of oscillating behavior. So theta will have some oscillating behavior. So what we want, that this oscillation should not be there, it should die out. So this should die out. So for that we want to include this damping term. So we want, like, we'll have this derivative PD controller, we can say. So if we have PD controller, we can have damping, and then we can have this stable closed loop system. Okay. So now let us suppose that there is a PD controller and this DC is 10 plus 2s. Okay, and we have this system 1 by 10 s square. Fine. So it asks that, okay, we know that, fine, let us see the closed loop system. So this transfer function is 10 plus 2s 1 by 10 s square by 1 plus 10 plus 2s 1 by 10 s square. So this should give 10 plus 2s 10s square plus 2s plus 10. Now from there you can see these are this positive constant for this characteristic polynomial. So we can say that, okay, the system is like stable. Okay, so this one is known. Now we are trying to find the steady state error. So it is asked what is the acceleration error constant. Now if you see the forward path, this 10s square into 1 by 10s square multiplied by 10 plus 2s. So there are two poles at origin in forward path. And by this internal model principle, we know that if in forward path we have, like, whatever the dynamics of this reference be, if it is a step, that is 1 by s. If it is unit step, it is, if it is a state with some gain, so k by s. So this forward path should have k by, like, 1 by s at least, so as to follow this one. Now up to what, like, dynamics it can follow. So if we have ramp as the input, then it can follow the ramp also. But if we have this k by s cube, that is parabolic input, then it will not be able to, this closed loop system will not be able to follow this one. So there will be some error. Now this error constant we have already dealt with it in previous, like, lectures. So we have this acceleration error constant, which is equal to limit s tending to 0 s square gs. We can say the forward path. Limit s tends to 0 s square. What is gs? This is 10 plus 2s by 10 s square. So what would it be? This will be simply be 1. Okay. This s square cancels and you get 2 by s. Okay. Yeah. So basically this, if you take limit, it will come out of like 1. So what is the error? This will be 1. So if there is a parabolic input which is being given, so it will try to track this, but there will be error which will be 1. Okay. Let us proceed to next part. So now it is saying that if the controller is a PI controller, that is Kp plus Ki by S, the system type with respect to reference input. So obviously, what you had 1 by Js square, and you have Kp plus KIS. Do we have KI by S? Okay. So this forward path is KPS plus KI by S into 1 by JS square. So there are three poles at origin, or we can say three integrator in the forward path. So what will be the type of system? Simply the number of poles at origin. So this will be 3. Yes. So now if this is third type system, so what do we expect? Since this is 1 by S cube. Now if parabolic input is applied, part of this input, that is K by S cube. So this will try to follow this one. This will follow this like input without any error. Okay. So now we have this PID controller. So we have seen what is the effect of PD, PI and proportional controller. Now we have this PID controller. Then we have disturbance also here. Okay. So systems type with respect to disturbance input is. So for this one, now if you see, this is the input. Now this would be the forward path and this is the feedback path. Okay. Because we are considering disturbance as input. So we'll consider this to be 0. This will be the feedback path. This will be forward path. Now this is not a unity feedback closed loop system. So we have seen that when we are saying type of system and this error constant, we dealt with this unity feedback system. So what we can do that if we have this G and if we have H in the feedback, then we can convert this to a unity feedback system. So what we just have, we'll have gain 1 added, gain 1 which is subtracted. So these two nullify their effects. Okay. So what we have this G. So this negative, and we want a negative unity feedback, no? So this is fine. And this one is positive. We can say this is H minus 1. So if you take this plus, so we can say this is minus and this minus 1. So this will be H minus 1 and this will be negative feedback, and we have a gain 1 and this is again added to this one with negative feedback. We have theta like R. Okay. So now we can simplify this. We can say, okay, G by 1 plus GH minus G. This is a transfer function. And we have 1 in feedback. Okay. So what we have done, we have a non-unitive feedback system, and We have converted it to unity feedback system to apply the concept that we have learned in lectures, we have understood in lectures. So now we say, okay, for this system, this one, like G and H in feedback, we say we can represent that with this one. So unity feedback gain and this one in the forward path. So for this system, where W is the input, like disturbance is the input, we can replace this by a transfer function in forward path, that is GS, and with unity gain in feedback. Now this G dash will be G by 1 plus GH minus G. So here G is what? G is this one and H is this one. So we'll just replace this. We find 1 by 10s square. What do we get? Something kind of, let me write it. Okay. So from this, we get that there is no pole at origin. So this is the characteristic polynomial, and there is no integrator in the denominator. So what is the type of this system with respect to disturbance as input? That will be 0. Now since it is type 0, that means it can, even if there is this one, if this is a step input, it would, this whole system will not be able to reject this step input. There will be some effect of this input on the output theta, that is the altitude. And so now it says that DC is 1 by 2, 1 plus 2 by s plus 3s. And what is the error constant? So we'll just have, what is the GS? So we have this forward path gain. Okay, so this is the limit s tends to 0. S square and G dash S, that is KD is 3 and KP is 2. KP is 1 and KI is 2. So this will be 0. Okay. So what can you say about this K, like parabolic error, or we can say acceleration error constant? From this, it should be 1 by 10. Okay. So that means we have done some mistake earlier. If you see this G, 1 plus GH minus G, what is the value of G? 1 by JS square. So obviously this not be S, this will be 1. Because JS square and the denominator of this one will cancel out. This will be like this. Okay. We will have this will go to 1. This will go to S square. Now we have cubic in denominator and square in numerator. So this will go to infinity because this all tends to 0. This will tend to infinity. Okay. Now this is like last question part. So we have a DC motor and this is described by differential equation y dot plus 60y equal to 600 VA. VA is the armature voltage and minus 500 W. W is the load torque, which is acting as a disturbance. Okay. So for this one, we can replace this by, like, we can convert it into Laplace transform. We say ys plus 60y equal to 600 VA minus 1500 W. So y is s plus 60 equal to 600 VA minus 1500 W. This implies y is 600 VA plus minus 1500 W by s plus 60. Now this you can represent using block diagram. So we have this 1 by s plus 60. And what is the input to this one? This is 600 VA minus 1500 into W. Okay. Now this is the output. This is the overall system with disturbance that is given. Now this system has to be controlled. That is the motor speed has to be controlled such that it tracks the reference speed. So for this, a controller is being used that is DC, and here it gives output VA, that is armature voltage, and input is error which is reference minus this output. So output is multiplied by 1. This is simply Y, and this is R. So R minus Y, this gives E, and this excites this controller, which gives the output VA. Okay, and VA is equal to, okay, this will be plus. So this will be VA equal to KPE plus KI E by S. So VA is equal to KP plus KI by S into E. So this one, this. Okay, so this is the overall closed loop control system where the objective is that this motor speed tends towards this reference motor speed, and for that this armature voltage is being changed based on whatever the error is between the speed. Okay, and for that this PI controller is being used. Now it says that the transfer function from W to Y, just load torque to speed, is a function of Kp and Ki and is given by this. So what is the value of this A, this constants A, B, and C? Okay. So we can find the transfer function with respect to this one. Let us see. So for this r is equal to 0. So this r is set to 0. Fine. And we have y from this transfer function. We know y is equal to 600 VA minus 1500 W by S plus 60. Now VA we know that is KP plus KI by S into E minus 1500 W by S plus 60. Okay, now this error is R minus Y, but since R is 0, error is simply minus Y. So this will be minus 600 Kp plus Ki S E or Y minus 1500 W by S plus 60. Okay. So let us simplify this. This will be S plus 60 into Y is equal to, we can just take it the right side, left side. This will give 600 Kps plus Ki by S into Y is equal to minus 1500 into W. Okay, now let's solve this one. So this will be S square plus 60S plus 600 Kps plus 600 Ki into Y equal to minus 1500 S. This will be multiplied this side into W. Okay. So what would be Ys by Ws? This would simply be minus 1500 S by S square plus 60, 1 plus 10 Kp S plus 600 Ki. Okay. So this is the transfer function. We have found out this is like kind of derivation, or you could have simply found by this one, since this is 0, this is the forward path, so G by 1 plus GH, where H is this feedback path transfer function. Okay. So what is being said, that the transfer function is AS by S squared. So what is the value of A? We have found out this is the transfer function. So A is simply 1500. Minus 1500, because this is minus 1500. So this is minus 1500. And what is C minus B? So C is C into Ki and B 1 plus 10 Kp. So here B is 60 and C is 600. C minus B is 540. Okay, so now you know what is the transfer function. Obviously, you know from this part what is the transfer function of the output from the disturbance. Okay, so now proceed to next question. So consider Ys by Ws, this transfer function, and compute the value of Kp so that characteristic equation of closed loop system have roots minus 60 plus minus 60 there. So this is minus 60 and these are the roots. Okay, so this is a closed loop system, poles. And we have to find the value of Kp such that this is satisfied. Now these are the poles. So what is the characteristic equation we get for characteristic polynomial? That will be s minus minus 60 plus j60 multiplied by s minus minus 60 minus j60. Okay, now we have to solve this. We'll get some polynomial. So let us solve this. We have two roots. So this poly command, not poly, poly. So when V is a vector, it is a vector whose elements are coefficient of polynomial, whose roots are element of V. So poly V, and to this command, V is a vector, and what is the output? This is the coefficient of polynomial whose roots are element of V. So we'll just apply the roots and we'll try to find out the polynomial. Right, poly minus 60 plus I 60 and minus 60 minus 1 120 70 200. So what is the characteristic polynomial? That will be s squared plus 120s plus 7200. So this is a polynomial. When we are writing closed loop transfer function, that is ns by ds. So whatever be the ns, ds will be s square plus 120s plus 7200. Okay, so this is what we know about this closed loop system. Now we had found the transfer function for ys given ws. This polynomial which is in denominator, this is the characteristic polynomial, and whether it be ys by rs or ys by ws, this 1 plus gh is same for all. So this characteristic polynomial is same for all. So if we try to find out y given r, you can say y given r, but here it is asked ws, so it's fine. So if we have this ws, so we have this characteristic polynomial, which is this one, s square plus 60 plus 10 kp plus 600 kl. S square plus 60, 1 plus 10 kp s plus 600 ki. This is the characteristic equation we found, and this is the one if roots are given. So these two should be equal. Implying to be equal. What we can say that 61 plus 10 kp is equal to 120 and 600 ki is equal to 7200. Okay, now if you solve this one, we get kp equal to 0.1 and ki equal to 12. So the value of kp and ki such that this ys given ws has poles at this one, these roots, complex conjugate root is 0.1 and 12. Okay. So this is same for input also, this R. So if we are saying that Ys by Rs has poles at this location, this is same. So what the response of this closed loop system to Rs will be defined by these poles, because this is a second order system and these are dominant poles. So it will be defined by this one. Okay. Is there any doubt in this one? This is the last question. So we are done with questions. If you have any doubt, you can ask. So basically through these examples, we are trying to understand the concepts that has been taught in week 7. And we have seen that the first few questions, we saw that how these terms like proportional, derivative, and integral coefficient affects, or we can say adding these poles and zeros at origin or the constant gain affect the behavior of the closed loop system. So this we saw, and then we saw that okay, if there is a system and we are saying that this system has to follow some desired property, means need to have some desired property, and since we approximate all the systems, we try to approximate basically by second order system with dominant closed loop poles. So we just neglect the poles which are farther from imaginary axis, and we say that okay, we'll just approximate it using the first order second order system. So in that case we can define the performance of system with zeta and omega n. So this value we get when we specify this rise time or peak overshoot or settling time in time domain, or we can say this resonant peak or bandwidth in the frequency domain. So through these specification given by the designer, suppose a designer like the, the person who owns this control system, that gives the specification to designer, and from these specification designer finds out what is the value of zeta and omega n that is required for the behavior given by these specified variables. So corresponding to that zeta omega n, this PID controller is tuned such that this behavior is obtained. And in doing so, it is also taken care of that when this disturbance rejection is accomplished. Because if disturbance is acting in such a way that, like, if it is acting and it is not rejected, then it will have effect on the output, and that is not what is expected. So this is all, and in that case also we the corresponding we all, it was also explained that okay, fine, that this is a PID controller and this is how it works, but realizing this derivative term is not possible. And when we are saying that realizing this marginally stable system, that is I term, is also difficult. So we said that okay, so we can approximate this PID behavior with compensators that we call this lead and lag compensators. And in the next week content, will it is discussed. So we'll deal with questions related to lead and lag compensators in next week problem solving sessions. Okay, I hope this week 7 content is clear to you. Okay, so any doubt you can ask, otherwise we can conclude this session. Oh, sorry. Vijay Sitaram Power. I didn't see your message, so you could have told, like, unmuted yourself and told. Okay, then. Thank you. You can leave now.